Eigenvalues, eigenvectors briefly last Thursday, and what I did say with eigenvalues, eigenvector is that the matrix A applied to a vector U. What does matrix A do to vector U? What does it do? What does that mean? Yeah, scalar multiplies it. Yeah, scalar multiplies it along the same direction. It doesn't change direction or exactly the opposite direction. Okay, so this is something like that. That's what it does. Yeah, AU in the same direction as U. Okay, where would this hold? Well, what vector is this going to hold? That's the one I'm going to ignore. Where does this solution hold? What we're going to do today is look at, determine the eigenvalues and eigenvectors of the matrix, okay, and look at some properties of eigenvalues, eigenvectors. I've explained why we need this in the last, on Thursday. Now, where is this true? Can you think of a vector where this is going to be true? Zero, yeah. The zero vector clearly is going to be true, isn't it? U is equal to 0. That is definitely true, isn't it? Yeah, okay. A times 0 gives you lambda times 0 gives you 0, doesn't it? Yeah, okay. So for eigenvalues, eigenvectors, we want non-trivial solutions. We want to make sure this is not 0. Okay, otherwise we might just, finish the course here, and just come back for the exam. Because there's nothing else to say about it. So we want to find solutions which are non-zero. Students go through all this procedures, okay? Work out AX, work out lambda, then work out the vector U, and they put 0, 0, 0. I go, why did you do that? You could have said that right at the beginning. Okay, the number of students who do that is significant. Please do not do that. Do not write down the zero solution. So for non-zero solutions, okay, lambda is called, this is called the eigenvalue. It's called the eigenvalue, okay? Pronounced eigen. Okay, that's how it's pronounced, eigen. And U is called the eigenvector. And we say, the vector U belongs to lambda, belongs to the eigenvalue, okay? And I'll talk more about this. Let's do an example. Let's do an example where, let's say we've got A is equal to 1, 1, minus 2, 4, okay, and U is equal to 1, 1. U is equal to 1, 1. Find the eigenvalue. So how will we find the eigenvalue in this case? How will we find the eigenvalue? Remember, we want to look at AU. We're looking at AU is equal to lambda U. So what do we get? We get 1, 1, minus 2, 4. Okay. On top of the vector 1, 1, what do we get? We multiply that matrix by that vector, or the vector by the matrix. What do we get? 1, 2, is it? 2. No, it's 2, isn't it? Yeah. 2, and 2, 2, isn't it? Yeah. 2 and 2. And what can you do with that? You can take the 2 out. You can take the 2 out and 1, 1. So then you've got A times U is equal to 2 times that same vector, haven't you? Yeah. So what's the eigenvalue equal to? 2. Of course, this implies that lambda 1, let's call this lambda 1, is equal to 2. Lambda 1 is equal to 2. Okay, let's do, say you're given that V is equal to 1, 2. Yeah? Now, what is AV equal to? AV is equal to 1, 1, minus 2, 4, 1, 2. What do we get this time? We want to multiply that vector there. What do we get? Row by column, remember, row by column. What's the first entry? If you apply this matrix's vector, what do you get? 2, no. 3, isn't it? Yeah? 1 plus 2 gives you 3, yep, 3. Yeah, minus 2 plus 8, yeah, gives you 6. What can you do with that? Yep, come on, Patrick.
3 out.
You can take 3 out, can't you? 3 is common. 3. And what do you get inside? What's the vector inside? Yeah, 1, 2, clearly. The same vector as that, isn't it? Yeah, okay. So what's the eigenvalue this time? Yeah, lambda 2 is equal to 3. So that's how you can work out the eigenvalues. If you're given the eigenvectors, that is. Of course, you're not normally given the eigenvectors, but you could be given the eigenvectors. So you do get more than one eigenvalue. Okay, let's do another example. Well, maybe I won't do it. Maybe I'll still. If you consider this, okay, how would you now find the eigenvalue of this matrix? It says show that matrix A scalar multiplies U, and find the value of this. You know, find the value. How much does it make it bigger or smaller? What does A do to U? We know. Well, we think if it's our eigenvalue, it's just going to scalar multiply it. How do we find this? How much it magnifies this number or this vector? Sorry. How would you do it? I mean, nothing's changed. Because it's 3 by 3 doesn't mean things have changed, does it? Just tell me how you do it. Yep.
So I think you would need to work out firstly what A and U.
AU, yeah, exactly. You have to work out AU, the multiplication of that, don't you? Yeah. AU, see what that comes to. If you work it out, you get 0, 2, 4, which gives you 2, 0. You get the factor of 2 out, 0, 1, 2. Okay. So what's the eigenvalue then? Sorry? 2, yeah, this time our eigenvalue lambda is equal to 2. So what does the matrix A do to you? Come on, hurry up. What does it do? What? Sorry, go on. Half? A, sorry? Increase the magnitude by what? By what factor? By 2, yeah, doubles, isn't it? It doubles the vector, isn't it? A doubles that vector, isn't it? A, you know, is 2 times that vector, yeah. So it's in the direction, but it doubles, isn't it? Yeah, okay. In 3D space, not in 2D, but in 3D space, clearly, yeah. Okay, let's go back. Let's have a look at the general eigenvalue, eigenvector problem. So you've got AU, okay, is equal to lambda U, yeah. So what do we get from here? You can write this as AU is equal to lambda IU. How can we solve this? Yep.
A is equal to 0.
No, it's not. A is not 0 vector. Yep. Yeah, you can take it to one side, couldn't you? Yeah, you can take everything to one side. Look, you've got a 0 on one side. That looks nice, doesn't it? We like solving problems with 0 on one side. Yeah. Okay. So we can write this as AU minus lambda IU is equal to 0. Yeah, can't we? Can write that, can't we? Yeah. Okay. What else can we do? You can factorize out the U. Yes, it's on the right hand side. So A minus lambda I U is equal to 0. Now we know we can't have U as we know for eigenvalues. What condition do we have? Go on, Steph. Sorry. Yeah, U doesn't equal 0, does it? U does not equal 0. We know that. Okay. Otherwise we won't have eigenvalues. You know, eigenvectors. Okay. And we've got lambda. Lambda is normally. I mean, Sylvester was the first person in 1852 to use lambda as an eigenvalue. Okay, he's the one who went to University or John Hopkins in Virginia. He's the one who caned the boy. You remember? And he was a bit of a psycho, like I said to you. I've described him anyway. And he couldn't graduate from the University of Cambridge because he was Jewish. Same Sylvester. Anyway, so what must you have? You want to have this solution, and you want non-trivial solutions. Okay. So you don't want the 0 solution. Yep. Yeah, it's where the determinant of that is equal to 0, isn't it? Okay. If you go back, if you look at what is it, exercise 6C, and you look at, you'll find that AX is equal to 0. Okay, this matrix. Okay, AX is equal to 0 has an infinite number of solutions, provided, or if and only if determinant of A is 0. Yeah, determinant of that bit there is 0, yeah? So we want to find the determinant of that is equal to 0, yeah? Okay? So we have got infinite number of solutions. So, or non-trivial solutions, or infinite number of solutions if and only if the determinant of A minus lambda I is equal to 0. Okay? And where do I get to? Okay, all right. So that's important. This is the thing we wanna. This is called the characteristic equation. Okay, characteristic equation, and that's what we want to solve. Now, there's two things you need to do for this to solve this eigenvectors, and these are two things you need to do. You need to solve that 7.2, okay, for lambda. Okay, you've got to solve this for lambda. Okay, you've got to solve that equation there for lambda. Find lambda, equate to 0. Now remember, determinant is a value, isn't it? Okay, it's a scalar. That's why you haven't got it underlined. Okay, and then you find the corresponding eigenvector by substituting lambda into this. Okay, so let's do some examples. First thing is eigenvalue, eigenvector. They come in pairs. They won't come on their own. They will definitely come in pairs. It's like a mother and child or mother and baby relationship. Why do you think it's a mother and baby? I'm going to dismiss that later on. But why do you think lambda and mu is a they definitely come in pairs? But why do you think I'm calling it a mother and baby relationship? It's a good analogy to make. Yeah, it does actually. The eigenvectors are born out of the eigenvalue. So you've got to first find the eigenvalue, yeah? You've got to first find, and if you're given the eigenvalue, it's different, okay? You've got to first find the eigenvalue, and then the eigenvalue, once you find the eigenvalue, then you can produce the eigenvector from the eigenvalue, okay? It's so you need to find the eigenvalue first. So let's do this example. Determine the eigenvalues and eigenvectors of A. Determine eigenvalues and eigenvectors of A is equal to 2, 0, 1, 3. So how do we find the eigenvalues, eigenvectors of this matrix here? How do we do this? Yeah, go ahead.
Well, we don't. So I think, should we go and maybe do the A minus?
Yeah, we do. Yes, exactly. We do that exactly. We have the determinant of A minus lambda I. We know this is equal to 0, yeah? So what is A in this case? Yeah, 2, 0, 1, 3. So the determinant of 2, 0, 1, 3, okay, minus what's lambda I? Yep. Yeah, 0 lambda, exactly. Okay, if you put lambda I, of course, is lambda 0, 0 lambda. Okay. Do you all agree with that? Yeah. Lambda times I is 1, 1. You multiply that by lambda, the ones. Okay. You multiply zeros by lambda, you get 0, don't you? Clearly, yeah. Okay. So, how do we simplify this? It's good to have it in front of me now. I can see what you can see, what you can't. Or you've got to keep on telling me. I can see in front what you can see, you see, with this thing. That's a great advantage. Sorry, go ahead. Yeah, 2 minus, exactly. I'm going to write down the first. 2 minus lambda. Okay, yep. Yeah, 0 minus 0 gives you 0. Quite right, yep. Yeah, 1 minus 0 gives you 1. And, yeah, 3 minus lambda. Okay, it's 3 minus lambda. So how do you find the determinant of this matrix? Yep.
2 times like 2 minus lambda by 3 minus lambda.
Yeah.
And then minus it by 0.
Exactly, yeah, exactly. One diagonal and take away the other diagonal, yeah? Okay, so this is 2 minus lambda times 3 minus lambda minus 0 is equal to 0. Yeah? Remember, determinant of A is equal to 0, doesn't it? For non-trivial solutions, you've got to have that equal to 0. So what's lambda equal to? Yep, Thomas?
2 and 3.
2 and 3, yeah. Lambda 1, eigenvalue lambda 1 is equal to 2, and lambda 2 is equal to 3. So now we've got, that's the eigenvalues. Now we've got to find the eigenvectors. The question says determine the it says eigenvalues and eigenvectors of A. So let's write down, let U belong, let's write it this way. Let U equal xy be the eigenvector belonging to lambda 1 is equal to 2. Let's call that one U, and we'll call the other one V or something, yeah? Okay. All right, how do we find the eigenvector then? How do we find, yep. Yes, exactly, yeah. We have A minus lambda I U is equal to 0, haven't we? Yeah, is equal to 0. Okay. Now A, of course, is given to us. A was 2013, and this time what's lambda equal to this case? 2, isn't it? Yeah, we've taken that value, haven't we? Yeah. So it's 2002. Okay. U we call it xy. Let's call it U is equal to 0. Yeah. What do we? If we simplify that, what do we get in the square brackets? If we simplify the square brackets, what do we get?
0, 0, 1, 1.
0, 0. 2 take away 2 gives you 0. 0 take away 0 gives you 0. 1 take away 0 gives you 1. And 3 take away 0 gives you 3 take away 2 gives you 1. Yeah, sorry, 1. Okay. X, y is equal to 0, 0. So what's the solution? What's the solution to that? What's the solution to that? Yep.
Well, the first one's going to be 0 equals 0.
No,
0 plus 0 equals 0.
yeah, of course. That's going to, yeah. If you expand the top,
Yeah.
you get 0 is equal to 0, which you.
Yeah, and then you get x plus 1.
Yeah, from the bottom. If you expand the bottom, sorry, the bottom row, yeah, your x plus y. That's the one you want to look at. X plus y is equal to 0. X is equal to minus y. So what's the solution to this then? Yeah, let y equal s. It can be. You're going to have infinite number of solutions to this. Okay. I can't find a solution to these. You're going to have infinite number of solutions. Remember, okay. We're looking at. You're definitely going to have infinite number of solutions to this. Okay. So let y equal s. Well, what? There's one value s can't be. It can be any real number, but it can't be one value. Sorry? Yeah, it can't be 0, yeah? Otherwise you're going to end up with 0, 0, aren't you? Yeah? Remember, for eigenvalue, eigenvector, you must not have the 0 vector, okay? Let s be any real number, but s does not equal 0, okay? So what's x equal to then? What is x equal to? If y is equal to s, sorry? Yes, minus s, okay? Minus s. So our vector u is equal to xy, okay, xy, which is equal to minus s, which means you can take an s out, minus 1, 1, where s is not 0, yeah? That is your eigenvector. A simple one would be, if you ask to find 1, take s to be 1, so minus 1, 1. Okay, but it could be minus 2, 2, yeah? It could be minus 3, 3. It could be, 1 minus 1, couldn't it? Okay, it could be anything along that line, minus 1, 1. All right, that's the eigenvector. This is a general eigenvector. Yeah, go on,
I
Patrick.
was going to say, I think you got this wrong in the book.
I don't think so. I might have 1 minus 1. That's okay.
No, you put the minus on the y-axis, not the x.
Yeah, it's okay. You can do it that way.
Oh,
As long as they're different, as long as they're in the same proportion.
okay, sorry.
Yeah.
Going off.
Yeah, no, you could, because 1 minus 1 gives you 0, yeah? -1 plus 1 gives you 0. Okay, either one will work. Okay.
Okay, yeah.
So no, it's not.
It's a fair
You-
comment.
No, it's not fair comment because I'm infallible. I cannot get things wrong. You should know that, Patrick.
Oh,
How
hang
can
on,
you-
sir, hang on. On your notes, you got 2 things wrong on your notes.
No,
You showed that?
no, you must have made a mistake. It can't be me. Must have been you, Patrick. Can't be me. I definitely cannot be me. Okay, now what else do we need to find? Yeah, and let V be a vector belonging to the other eigenvalue. Yeah, okay. Let V. Let's write this. Same procedure, exactly the same procedure. Nothing changes. Okay. We can call it x. Let V equal xy. Different xy, not the same one. Okay. Different xy. Okay. The reason why I call it xy is students like to solve equations with x and y's in rather than a's and b's. I could call it a and b, but I want to call it x and y. We've got different xy this time. So how do we find the v this time? How do we find the eigenvector this time? Same procedure, which is we want to find a minus lambda I v is equal to 0. Okay. That means what do we do? A, what was that? A was, where is it? 2. Yeah, 2, 0, 1, 3. And this belongs to this. What's the mother of this vector? What's the mother of this eigenvector? Come on. Where does it belong? Who does it belong to? What eigenvalue does it belong to? Remember I said the eigenvalue was the mother and the eigenvector was the child of the baby. Yeah, go on.
Would that be the 3?
Yeah, of course, belongs to lambda 2 is equal to 3. Okay, so this time we have minus. So what do we have? Minus what? Yeah, minus 3, 0, 0, 3. Okay, you put I in there. Okay, and your V is equal to 0. You simplify that, what do we get? If we simplify this, the square brackets, you should be able to simplify that. What do we get? Go on.
So we get -1.
Yeah, 2 minus 3 gives you -1. Yep.
0.
0. Yep. Okay.
1.
1 minus 0 gives you 1. Yep.
Then we get 0.
Yeah, 3 minus 3 gives you 0. Okay. X and Y is equal to 0. 0. Yeah. So what do we get? What's going to be an eigenvector for this? What do you actually need? Think about it. Okay, let's put the first one down. Minus x is equal to 0. X is equal to 0. What can we say? What's that going to force x to be?
0.
0. X can be 0, yeah? X has got to be 0, okay? You've got to have x. This implies x is 0. What about y?
Well, y's got to be 0.
No, you can't. If you have 0, then you can have the 0, 0 vector. And remember, for eigenvalue, you cannot have the 0, 0 vector.
Right.
So what's y going to be?
S.
Yeah, any real number apart from 0. Y can be any real number, can't it? Be 2, 3, 4, 5, 6, 7, 8.
Okay.
Call it whatever you want, apart from 0. Okay? And also, y is equal to s, where s is not 0. S is not 0. So my eigenvector, or belonging to this mother, okay, 3, v is equal to x, y, okay, is equal to x, y, and this time x, y, x, of course, is 0, and y is s, which is equal to s, 0, 1, yeah? Where s is not 0, yeah? You can't have 0, remember, where s is not 0. Okay, so you've got 2 eigenvalues and 2 eigenvectors, and if you plot them, with v, the last one, remember the eigenvalue was 3, wasn't it? Yeah. So it's going to be AV is equal to 3v. Yeah. Okay. What was the eigenvector belonging to u? What was that? 2. So it will be AU is equal to 2u. Now if you plot them, the eigenvalues, I'll put it simple one. The case is equal to 1. But you know, you don't have to. Here they are. Here they are. There. Sorry. Let's do this. This is what you get. Yeah. AV. Remember, this is the 0, 0, 1 vector, isn't it? Yeah. 0, 1. It goes up there, doesn't it? Yeah. Okay. It goes up there. Here, 1 minus 1 or whatever, or minus 1, 1, whatever way. Okay. It's going to go in that direction. Yeah. Okay. Minus 1. The one Patrick was saying, minus 1, 1 will be up here. Yeah. It'd be in the same line, wouldn't it? Yeah.
Yeah.
Same line. It's got to be the same line. Okay. So you know, that times it by that triples it, and this one doubles it. Yeah. Okay. So that's your eigenvalues, eigenvectors. Now let's do a 3 by 3. The only thing you want to be careful with 3 by 3 is the number of negative sides you get. So if you get minus times minus, okay, you often end up with. Hang on, we're going to do this one. You often end up with something like this, expanding. Something like that. Minus 1 minus lambda, yeah? Oh, whoops.
That's a bit too far in, sir.
Yeah.
So fast.
Yeah. No, I'm trying to zoom out of that. Is it any better?
No. You've got it right in front of you, you can see.
I'll turn this